Okay, so I know that Smith hasn't said much about this concept of logical equivalence, but I think it's actually really important. I think he does mention it later, but I think it's good to talk about it a bit earlier. It's a really important concept, and it's really not that complicated, so it's good to talk about. So let's review a few things. So the first is just, some of our jargon, right? Truth value is just whether a statement is true or false. And for the purposes of logic, we assume that every statement does have a clear truth value, right? In the real world, this is debatable for reasons I'll talk about in a little bit, but in logic, we make this simplifying assumption. It's clear every statement gets a big old T for true or a big old F for false, right? It's one or the other, one or a zero, right? Statement either true or false, T or F on a truth table, right? Again, in real life, it might not always be this clear, right? Think of a man losing his hair. Is he bald or not? Sometimes yes, very clear he is. Sometimes no. If you watch Game of Thrones, Varys, who doesn't have a hair on his head, definitely bald. Khal Drogo, who's just so much hair on his head, definitely not. The guy who plays Stannis Baratheon, who knows? We will overlook those sorts of unclear cases for logic. We, as a simplifying assumption, will say it's either true or false. We give it one value or the other. Again, maybe not that simple in the real world, but in logic, we're trying to make things simpler and more precise. Now, truth conditions. Truth conditions are when a statement is true or false, right? When is it that this statement is true? When is it that it's false? And let's review the truth conditions for the statements we've talked about in propositional logic, right? A and B true when both A and B are true, false otherwise, right? A or B true when at least one of those two statements is true. Remember, we're using the inclusive or. Not A true only when A is false, right? And we can look at the truth tables for these statements. A and B true only on this top line of the truth table where A and B are both true. A or B true on every single line except the bottom one where they're both false, because for this to be true, only one of these statements needs to be true. Not, a little tilde symbol, just always has the opposite value from whatever it negates, right? When A is true, not A is false. When A is false, not A is true. All right, so that's just a little review. But let's get to a seemingly complicated, perhaps tricky statement. It's simple, but there's something about it that's tricky, right? So let's look. How would you symbolize this particular argument? Bob and Sarah did not both go to the party. I won't go through the whole symbolization, right? Our propositions would be Bob went to the party, Sarah went to the party, Would you say not B and S, or not B or not S, right? Think about this. Which of these would you use for this sentence? This first one or this second one? Give it a second's thought. Which do you think is better and why? Well, it's a trick question because either of them works. They're honestly equally good. Why does either statement work? Well, in one sense, because when you think about them, they kind of mean the same thing, even in ordinary imprecise English, right? When is this statement true? Well, it's true whenever B and S is false, and B and S is false when at least one of them didn't go, right? When is this one true? Again, when at least one of them didn't go. Now, if I were going to be real hair splitting, I would probably give the mildest of mild preferences for this first one, because, you know, this one uses an and. This one has our and symbol. But honestly, it does not matter on a test. Either would be right. Why? Because they are true in exactly the same cases. When they're true when one of them didn't go, and they're false in exactly the same case when in fact both of them did go. If you don't believe me, look at our truth table, right? There's only one case where both these statements are false. It's when both of them went to the party. Every other case we sketch here, both are true. Not S and B is false whenever not S or not B is false, and it's true whenever not S or not B is true, right? And vice versa. When when one is false, the other is false. When one is true, the other is true. Another way of saying this, they have exactly the same values on every single line of the truth table. Another way of saying it would be that they have exactly the same truth conditions. Statements like this that always have the same truth values on the truth table are logically equivalent. For the purposes of logic, they mean exactly the same thing, right? Now look, as Smith has already made clear, we might lose a little bit of the information we have in ordinary English when we translate into logic. We can argue maybe these statements in ordinary English would have a slight, they might tell us something about the speaker, or they might have a connotation or something that they don't in logic. That's not important, because all we're thinking about are the truth conditions, and if they have the same truth conditions for purposes of logic, they mean the same thing. Well, and when two statements mean the same thing in logic, you can always replace one with the other. And it doesn't just have to be two statements. You might, and we'll see some examples of this later, you might have a case where three different statements mean the same thing. You can just replace one with the other. Now, why is this important? Because logic, as you guys have probably noticed, especially formal logic, is very, very persnickety about its rules, very, well, inflexible at times, right? And a lot of times it might be easier to work with one sort of statement than another. If that is, we replace it with the logically equivalent one, that might make our life a lot easier, right? Another reason this will be important in a few weeks, when we get to the so-called tableau method of testing validity, we will use this idea of logical equivalence quite a lot, right? Smith talks about the idea more there, but I think it's good to already have it in mind. It's one of those things that doesn't hurt to talk about multiple times. So, not A and B, not parentheses A and B parentheses, is logically equivalent to parentheses not A or not B close parentheses. And to other statements using nots and ands are equivalent. Not A and not B is logically equivalent to not parentheses A or B close parentheses. Think about it. Each of these is only true when both A and B are false. Yeah, look at our truth table, right? On every single line except the bottom one, both of these statements have an F. They are false. On the bottom line, both have a true. In every possible case we can imagine, these statements have the same truth value. They mean the same thing. They are logically equivalent. Now, these rules about this are actually called De Morgan's rules. You know, these three little bars, you'll see these sometimes, they mean logical equivalence. Not A and B, equivalent to the not A or not B. We can always replace one with the other. You can almost think of this as a way of distributing the not, right? You distribute it and you change the and to an or vice versa, right? But, just know that they're logically equivalent. One other very important logical equivalence is double negation. Not A is logically equivalent to A. Right? Not A is true whenever not A is false. Well, that means it's true whenever A is true, right? And it's false whenever A is false. And this goes for any statement you might put double negation in front of. We're just using the A here because that makes things easier. All right, so hopefully this idea of logical equivalence makes sense to you guys. We will come back to it. We'll talk about it a lot more. When we get to the conditional in a few weeks, it'll come up, and it'll be very important when we talk about this tableau method of testing for validity toward the end of the course.